All right, welcome to Chapter 5, Section 1. Lecture 19 is what we're on. Parte 2. Okay. Left off last time with our discussion of energy. We talked about potential energy and kinetic energy and so on. Now I want to talk about the differences between heat, thermal energy, and temperature. Thermal energy is the one we discussed last time. Thermal energy is the energy of random motion of particles. Okay, so every substance out there is made up of particles, whether atoms or molecules or ions or whatever, and they are always in constant random motion. Okay, constantly moving. Some this way, some that way, what have you. And the hotter something is, the faster those particles are moving in their random directions, bouncing off one another, and so on. Okay. So thermal energy, it's hard to get a good total quantification of that, just because there's an indescribably huge number, well, it's describable, but it's still an incredibly huge number of particles in any given object. And they're all moving randomly. Some are going to be moving a little faster, some are going to be moving a little slower, and so on. But we can come up with a statistical description of that, and so on. It's like we talk about how much energy each particle has, or, no, I got that wrong, oops. So how much energy each particle has, and the number of particles that have that energy, and you can come up with a description that looks like that, such that, there's a very small number that have high energy over here on the right, a small number that have very low energy here on the left. Most are going to be somewhere in the middle. Okay. And in the end, you're still not going to talk about the total thermal energy of any object too much, because what really matters is the average, and that is where temperature comes in. Temperature is proportional. That's what this sign means. It means proportional to the average kinetic energy. Oops. Those angular brackets there, we use that to mean average. So what that means is that the higher the temperature of an object, the higher the average kinetic energy of the particles is going to be. That's all. So if this is medium temp, then this would be, high temp, where the average is further to the right. And this would be low temp, where the average is, oops, that's awful. The average is further to the left. Okay. So low T and high T. Okay, so temperature is the measure of the average kinetic energy of the particles of the object. And temperature is a much better description, not only because it's easier to measure than the total thermal energy of the object, but because a lot of the basic function of the universe is built around temperature rather than thermal energy. Okay, if you have a really cold, let's see, this is cold and this is hot, the big cold thing will have more thermal energy, and the small hot thing will have less thermal energy, just because, fewer particles versus more particles. But what really matters is the temperature, okay? What'll happen over time is that temperature will flow from the small hot thing into the big cold thing until they're both at the same temperature. So temperature is a lot more useful for several reasons there. It's easier to measure, and it's more related to the way the universe functions. So overall thermal energy, you can talk about that. And it is somewhat important, because now we talk about heat. heat is the transfer of thermal energy. Okay, so anytime thermal energy moves between two objects, you're talking about heat. Okay. And so we represent heat, that's another important thing, we represent heat by Q. Okay. So Q means heat. Okay. It can also mean charge, which will occasionally be confusing, but it's just one of the things you're going to have to deal with. You know, there's only so many letters, and we repeated ourselves a couple of times sometimes. So Q means heat. And heat is the transfer of thermal energy from one place to another. There are different ways this could happen. Your elementary school might have been different from mine, but I recall we talked about conduction, convection, and radiation as the three different ways that heat can be transferred. So convection means matter and energy are moving from one place to another. So convection, you can think of hot air rising above a fireplace. Okay, the hot air is rising, and it's taking thermal energy with it. Okay, so there's heat there. There's a movement of thermal energy from the hot fire into the cold air above the fire. Okay, conduction is just energy that's moving between touching objects. Okay, so matter is not moving, okay, but energy is. Okay, so this example down here in the lower right, okay, that was a matter of conduction. Okay, heat was being transferred between the two objects, but all their particles were staying where they were. And finally, we have radiation, where objects are not touching, so no touch. Instead, it's just electromagnetic energy. Okay? So light and heat are being transferred, are carrying the energy from one place to another, and that's how you're getting the transfer of heat. Sunlight is an example of that, or if you're warming your hands in front of a fireplace or a stove or something like that. Those are examples of radiation. And all three of those, conduction, convection, and radiation, are forms of the transfer of thermal energy. Those are examples of heat. All right, now that we've talked about thermal energy and heat and temperature a little bit and differentiated them, let's talk about the units of energy. Historically, the unit of energy was the calorie. That comes from Latin. Calor means just heat in Latin. So the calorie is the unit of heat, or was the unit of heat. And 1 calorie equals the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Okay. So if you had 1 gram of water, you raise the temperature from 25 to 26 degrees, you've put in 1 calorie of heat. Now, there was also the unit, the calorie, where 1 calorie is equal to 1,000 calories. No, you have not had a stroke. You're not hearing things. I just said that 1 calorie is 1,000 calories. But you'll notice that this here on the left is an uppercase C, this here on the right is a lowercase c, and that's how they differentiated them. Nowadays, sometimes when they still use the calorie, they'll call it a kilocalorie. But the only place we ever really still use the unit of the calorie is, once again, the U.S. government when talking about the amount of energy stored in food. And if you're curious, yes, our food is using the kcal, the kilocalorie, 1,000 capital C calories when it's talking about the energy stored in our food. They measure that by burning the food, by the way. Nowadays, we no longer use the calorie. These days, the SI system unit is the joule, named after yet another dead guy, where 1 joule is equal to 1 kilogram meter squared per second squared. That probably doesn't make a heck of a lot of sense. So instead, let's talk about it as, equaling 1 Newton meter. Remember, whether you remember or not, a Newton is kilograms meters per second squared, or mass times acceleration. So Newton is a measure of force. It's the amount of force necessary to accelerate a particular object. So in the case of 1 Newton, that would be enough force to accelerate a 1 kilogram object. It's a rather hefty chunk of metal, a rather significant amount of matter. It's about 2.5 pounds, or 2.25 pounds. That's enough to accelerate, 2.25 pounds by 1 meter per second every second. And a meter is, of course, about 3 feet. So starting at, from a standstill, 1 Newton of force will accelerate, a brick to about 3 feet per second. It's, chucking it at a fairly significant velocity. All right, so the times meters here, that means that you're applying that force across a distance. Okay, so you're not just applying it once and then stopping, you're applying it along a certain distance. Okay, so one way to think about a joule is you have that 1 Newton object, a brick that weighs, 1 Newton. Newton is a measure of weight rather than of mass. And so a 1 Newton mass in Earth's gravity, the gravitational acceleration of Earth is 9.81 meters per second squared. So the mass of 1 Newton object is going to be about 100 grams. So think 2 eggs. So if you take that 1 Newton object and you lift it up from the ground and put it on top of a washing machine, then you have exerted 1 joule, or you've done 1 joule of work. Okay, you've increased the potential energy of those 2 eggs by 1 joule. Okay, that's what a joule is. A joule is actually a very small amount of force, because eggs are tiny and gravity is weak. When it comes to chemical reactions and stuff, they release hundreds of thousands of joules of energy for, just a few grams of chemical reactant. So a joule is actually very, very small, but it's based upon the basic SI units, which is why it is helpful. For those of you who want to do conversion for some reason, 1 food calorie, that is to say 1 capital C calorie, 1 kilocalorie, is equal to 4,184 joules. Okay, that's the full name. The unit is abbreviated just J, capital J. Okay, so 4,184 joules is equal to 1 kilocalorie, or 4.184 joules is equal to 1 lowercase c calorie. And now to give you another example, a cup of water, or about 355 milliliters, or about 355 grams. How much energy would it take to raise that from 25 degrees Celsius to boiling? That is 111,399 joules of energy. And in a couple of lectures, by the time we're done, you will know how to do that calculation yourself. Won't that be nice? But the fact is that we usually work in kilojoules for most of our stuff, just because a single joule is a very small amount of energy. And the next bit of our lecture will actually be fairly math intensive and so on. So I'm going to go ahead and save that for the next video. That means that we are done for this particular video.